next video is about limits. Okay, so remember the sequence that we saw, a sub n equals a sub n over n plus 1, right? And if you compute the terms of the sequence that we saw, it's 1 over 2, 2 over 3, 3 over 4, and then you can go like 100 over 101, or 1000 over 1001, and you can keep doing like this. Okay, if you compute the number, the floating point or the decimal expression of this is closer and closer and closer to 1. Okay, and if you this is like 1/2. Okay, if you plot the numbers of the sequence, you start like here, and then you are going like this and this, and if this is 1, you're getting closer and closer and closer and closer to 1 as n goes to infinity, right? So it never really gets to 1, but it gets as close to 1 as you want. Okay, so the sequence for values of n that are very large, it will be very close to 1 all the time. Okay, so that's what we mean by a limit. Okay, so this is some sequences will behave like this. They will approach a number and will stay close to that number, and closer and closer and closer and closer to that number as n increases. Okay, so that's the limit. Okay, so the rigorous definition of the limit is this one. So we say the real number a is said to be the limit of the sequence a sub n if for any real number epsilon greater than 0, it doesn't matter how small epsilon is, there is an index n, capital N, which may depend on epsilon, such that for every natural number n greater than this capital N, this threshold or index, the sequence will satisfy this inequality. The absolute value of the difference between a sub n minus a is smaller than epsilon. Okay, and then we call this sequence to be convergent. Okay, so this is just the mathematical rigorous way of saying the same thing that I said with this example. Okay, what we mean is, suppose we well, let me apply the definition to this sequence, and let's see if this is clear. Okay, so suppose we choose any number epsilon greater than 0. Okay, it doesn't matter which number we choose. Okay, so we were saying that this sequence, it kind of approaches this number 1. Okay, so can we say if the limit of the sequence is 1? Okay, we need to prove that this is true for given threshold. Okay, so we need to prove that a sub n minus a is smaller than epsilon for a given n greater than capital N. Okay, so a sub n, let me go here, a sub n is n divided by n plus 1 minus 1, and this is n minus n minus 1 over n plus 1. Okay, and the absolute value of this is just 1 over n plus 1. Okay, so this has to be smaller than epsilon. Okay, well, this is true if, and then we kind of multiply and divide by n plus 1, so we have 1 over epsilon smaller than n plus 1, right? Or if we write it in another way, we have n is greater than 1 over epsilon, and then minus 1 that goes. Okay, so if we choose capital N to be 1 over epsilon minus 1, right, then for every n greater than this capital n greater than this thing is true. A sub n minus 1 is going to be smaller than epsilon. Okay, so this is the proof. Now we can say that this sequence has a limit that is 1. Okay, and if it's too abstract for you, let's kind of think, write it with some examples. Suppose epsilon is 0.1, then if n is greater than 1 over 0.1 minus 1, so this is 10 minus 1, 9, if n is greater than 9, what we are saying is that the difference between a sub n minus 1 is going to be smaller than epsilon. Okay, so in this case, a sub n with n equals 9, so let's take a n equals 10. So a sub 10 is 10 over 11. Okay, and so we're saying is that 10 over 11 minus 1, which is 1/11th, is smaller than epsilon, which is true, right? Because epsilon is 1 over 10 and 1 over 11 is smaller than that, right? Is it clear? Suppose instead of 0.1 we chose epsilon 0.01, right? Then we have n has to be greater than 1 over epsilon minus 1, but 1 over epsilon this is 1 over 100, so this is 100 minus 1, 99. Okay, so we take a 100, this is 100 over 101. We're saying that the difference between this and 1, the absolute value of the difference, in this case 1 over 101, is smaller than epsilon. Okay, in this case, which is true again. Okay, and if you think about it, we can take epsilon smaller and smaller and smaller, and this with this formula we can find the value of n, or the term of the sequence that we need to find in order to find a term that's closer to the limit than this value of epsilon that we have chosen. But the interesting thing is that this makes sure that every term after this, okay, so a to a 101, a 1000, a 10,000, whatever, all of them will be closer to 1 than epsilon. Okay, so this is always going to be true. Doesn't matter which value of n we choose, there is always going to be a capital N index after which every term of the sequence is going to be closer to the limit than this value of epsilon that we have chosen. Okay? Okay, so some sequences do not converge to a limit, but they go to infinity or minus infinity, for instance. So for instance, if you have the sequence a sub n equals n, okay, the sequence of real numbers, it doesn't matter how high value of n you give, you will always get a higher number, right? So this is not getting closer to any real number, it's actually growing and growing and growing and growing and growing. Or if you have a sub n, n squared, this is growing faster, right? So this is what we want to catch with this definition of a divergent sequence. Okay? So we say that the sequence a sub n is divergent to plus infinity if for any real number c greater than 0, okay, it doesn't matter how large c is, then there exists an index n, which may depend on c, just like before, such that for every n greater than capital N, the sequence satisfies the inequality a sub n greater than c. Okay. And likewise, it is said to be divergent to minus infinity if for every real number c smaller than 0, there exists an index n, capital N, such that for every n greater than capital N, the sequence satisfies the inequality a sub n smaller than c. Okay? And yes, so I forgot to say that when we have the limit of a sequence, so we have sequence a sub n goes to a as n goes to infinity, we write it like this: the limit when n goes to infinity of a sub n is a. Okay? Well, when a sequence is divergent, we say that the limit when n goes to infinity of a sub n is plus infinity or minus infinity, if that's the case. Okay? Okay, so now let's see some examples. We have the sequence a sub n to the p, okay, where p is a real number, is divergent to plus infinity if p is greater than 0, and it's convergent if p is smaller or equal than 0. Okay, so we will apply the definition. Start first with the p greater than 0. Okay, so we have a sub n is n to the p. Can we find a c such that n to the p is greater than c for after a threshold that we choose? Okay, well, we can manipulate this. This means that n has to be greater than c to the 1 over p, right? So if we have capital N greater than c, or we choose like this, equal 1 capital N equals c to the 1 over p. Okay, let me write it better. If we choose n such that it's greater than this threshold value that we have chosen, then every value after this will be greater than this, right? So we have a sub n is greater than c if n is greater than c to the 1 over p, right? So that proves this first part. Okay, applying the definition, we have found a c such that this is true. Now let's go for the other values of p. What happens if p is equal 0? P equals 0, then a sub n equals 1, right? So this is kind of trivial, but the limit when n goes to infinity of a sub n is just 1, okay? Because every term in the sequence is 1, okay? Now, suppose p is smaller than 0, okay? P is smaller than 0. Then what I'm going to say is that, so a sub n is n to the minus q, where q is minus p, right? So this is a sub n is 1 over n to the q, okay, where this is growing to infinity. So what I'm going to prove is that this goes to 0, okay? The limit of the sequence is 0. How do we prove this? Well, applying the definition again. So we have a sub n minus 0, which is the same as a sub n. This is just 1 over n to the q. Is this smaller than epsilon? For any epsilon that we choose, then just like before, this means that that n to the q has to be greater than 1 over epsilon. Or in other words, that n has to be greater than 1 over epsilon to the 1 over q, okay? So if we choose n equals 1 over epsilon to the 1 over q, for every small n that is greater than this capital N, the difference between a sub n and 0 is going to be smaller than epsilon. In other words, a sub n minus 0 smaller than epsilon if n is greater than 1 over epsilon to the 1 over q, okay? So we can write this like this: the limit when n goes to infinity of a sub n is 0, okay? So let's just recapitulate. If a sub n equals n to the p, right? It's going to be divergent to plus infinity if p is greater than 0. It's going to be convergent to 1 if p equals 0. And it's going to be convergent to 0 if p is negative. Okay? And finally, some sequences are not convergent, neither divergent. Okay, so for instance, if you have this sequence a sub n equals minus 1 to the n, which is this sequence minus 1, 1, minus 1, 1, minus 1, 1, and so on. This sequence is not approaching any number because it's just going from minus 1 to 1, minus 1, 1, minus 1, 1. So it's alternating between two values, but neither it is growing to infinity or decreasing to minus infinity. Okay, so these kind of sequences are called non-convergent or you could say they're neither convergent nor divergent. Okay, doesn't matter. Okay, so proposition: if the limit of a sequence exists, it's unique. Okay, this is a very simple proof. Suppose we have two particular limits. Suppose that this was not true. Okay, so we're going to prove by contradiction. Okay, suppose we have a number a. It's called the limit when n goes to infinity of a sub n, and then a number b, limit when n goes to infinity of a sub n. So okay, two different limits, and let's suppose a is smaller than b. Okay, this is not important, but just suppose. Okay. Now, according to the definition of the limit, then we have a sub n minus a is smaller than epsilon for some n greater than capital N sub 1, and then a sub n minus b is smaller than epsilon for some n greater than n sub 2. Okay, so then we have the difference between a minus b. Okay, is just suppose we have n greater than the maximum of n sub 1 and n sub 2. Okay, so both conditions apply. Now, if we compute the difference between these two numbers, then we can apply this trick: subtract and sum the same number. Okay, this is the same because we're summing and subtracting the same number, and applying the definition of one of the properties of the absolute value. This is just smaller than this plus this, right? This is the triangular inequality. But we know that this is smaller than epsilon because we're taking a very large index that's greater than these two. So this is smaller than epsilon and smaller than epsilon. So this is smaller than 2 epsilon. Okay. So the difference between the two limits is as small as we want it to be. Okay, we can choose very small numbers, epsilon, and so that we can make this smaller. So in other words, that the limit when n goes to infinity of a minus b is 0, which implies that a equals b. Okay, so we have proven that a equals b. So it doesn't matter this original assumption, it's not valid. Okay, so it can't be true. Okay, the limit is always the same. Okay. Now, proposition: every subsequence of a convergent sequence has the same limit as the sequence. Okay, this is kind of obvious. Okay, because a subsequence is a sequence that is contained in the original sequence, so you cannot go to a different limit than the original one, right? So I hope this is clear for you guys. So if you compute the limit to a general sequence, any subsequence that you can find will always have the same limit. Okay. Now, it's not always easy to compute the limit of a sequence using the definitions as we have done before. Okay, but so that's why we have these rules that I'm gonna explain now. Okay, these are kind of computation rules for limits. Okay, so first proposition: suppose or let a sub n and b sub n be two convergent sequences. Okay, with limits a and b. So that means that a is the limit when n goes to infinity of a sub n, and b is the limit when n goes to infinity of b sub n, right? Well, the limit of this sequence, that's the sum of the two sequences, or the subtraction. So suppose we have a new sequence that's computed like this. Okay, so this is just like when we summed functions. The new sequence is just the sum of the two terms. Okay, well, the limit of c sub n is just the sum of the two limits. Okay, so just like I'm saying, if the limit of this, the sum is the sum, the limit of this of the subtraction is the subtraction. If the new sequence is, instead of the sum, is the product, okay, a sub n, b sub n, then the limit when n goes to infinity of c sub n is just the product of the limits of the two sequences. Okay, and the same with the quotient between two sequences just as long as this makes sense. Okay, the sequence in the denominator is never 0 and the limit is not 0. Otherwise, it doesn't make sense. Okay, this definition. Also true, the limit of a sequence that's exponentiated to a different one is the limit of the basis exponentiated to the limit of the exponent, and the limit of the logarithm of a sequence is the logarithm of the limit. Okay, well, I'm not going to prove these ones, but they're very useful for our problems. Okay, so just take them in and study them with care. Now, next rule is what we call the sandwich rule. Okay, so suppose we have the limit of a sequence a sub n, it's called L, and another sequence c sub n is also have the same limit. Okay, for all, and we have that for all n greater than a given threshold capital N, so given some number or natural number, we have this bound. So we have the sequence a sub n is bounding from below this sequence b sub n, which is bounded from above by c sub n. Well, the limit then, the limit of b sub n is going to be equal to L. Okay, if you can think about it, if we take limits here, limit of a sub n, limit of b sub n, and the limit of c sub n, then this is L. Okay, we have said, and this is also L, right? So this is L and L. So the limit of b sub n is between the same number. Okay, so it's smaller or equal than L and greater or equal than L. So that means that this is L as well. Okay, so remember that one, the sandwich rule. And then finally, the final rule for computation is that every monotonically increasing sequence bounded from above converges to some limit. Okay, and also the same if a monotonically decreasing sequence bounded from below converges to some limit. So suppose you have any sequence that's this is 0, this is some value c, right? And this is a sub n. So we have, suppose we have something like this, and it's growing, it's growing, it's growing, and it's monotonically increasing, right? We know it's every term is going to be greater or equal than the one before. Well, if this sequence is bounded from above by any number, we know we can prove that this is going to be converged to a limit. Okay, the proof is actually very interesting, but we are not going to see it here. But just believe me that, right? That this is going to get closer and closer and closer and closer to a limit. It can't, obviously it can't grow to infinity, right? Because it's bounded from above. And it's not going to be alternating either, so it's because it's monotonically increasing. So it's going to be convergent to a given limit. Okay? And so, yeah, the proof for this is in the lecture notes if you're interested in. Okay? So, let's see. So let's use those rules what we had just seen. So these ones, okay? This sum, product, quotient, power, logarithm rules, sandwich rules, and this monotonically increasing bounded sequences convergent to compute some limits in some examples. Okay? So first one, let's say a sub n is the sine of n over n. Okay, so this is just the quotient of two sequences, right? B sub n sine of n, and then c sub n is n. Okay, so B sub n is not a convergent sequence. It's actually a non-convergent sequence, right? The sine of n is going to be like something that oscillates between -1 and 1. And t sub n is a divergent sequence. It diverges to plus infinity, right? So we can't use the property that the limit of a sub n is equal to the limit of b sub n divided by the limit of c sub n, because these two limits do not exist, right? But we know that the sign, so the absolute value of the sign of n is going to be smaller than 1, right? Or in other words, that the sign of n is going to be between minus 1 and 1, right? And so if we divide everything by n, right? So then we have minus 1 over n is smaller or equal, and then this is a sub n, and then this is smaller than 1 over n. If we take limits in both sides, then this is, well, let me write it like this. The limit of this is going to be 0, okay? This is the limit when n goes to infinity of a sub n, smaller than the limit of this, which is 0 again. So if we apply the sandwich theorem, okay, to this inequality, we can say that a sub n, this sequence sine of n over n, has a limit that is 0. Okay? Okay, let's see the next example. Suppose a sub n, let's define the sequence by a recurrence, okay? So that you know how to deal with them. A sub n plus 1 is equal to 1 over 2 times a sub n plus 6, with the first term a sub 1 equals 2. Okay, so the first thing to do when you have recurrence relations like this, or is to try and write out the first terms of the sequence, okay, so that you can get a feel of how they go. Okay, so this is 2, and then a sub 2 is 1 over 2 times 2 plus 6. 2 plus 6 is 8, over 2 is 4, and then 4 plus 6 is 10, over 2 is 5, and then 5 plus 6 is 11 over 2, so then you have 11 over 2, and then you have 11 halves plus 6 over 2, it's 23 over 4. If you don't believe me, just do it. And then 23 over 4 plus 6 over 2 is 47 over 8, and so on. Okay, and if you write the decimal approximation to this, this is 5.5, this is 5.75, this is 5.875, and if you keep computing terms, you will see that this is going to be closer and closer and closer to 6. Okay, so is this sequence convergent to 6? Well, first of all, we need to show that it is bounded, okay, so that a sub n is smaller than 6 for all n, okay. How do we do this? Well, normally using induction, okay. So remember induction, we prove that this is true for n equals 1. So for n equals 1, a sub 1 is 2, which is smaller than 6, okay. Now we suppose it is true for some n, and see if it's true for n plus 1, okay. So a sub n plus 1 is 1 over 2 a sub n plus 6, but we are supposing that a sub n is smaller than 6, right? This is the induction hypothesis. So this is smaller than 1 over 2 6 plus 6, so this is smaller than 12, which is 6, 12 over 2, sorry. Okay, so this we have proven using induction that this sequence is bounded from above, right? Now, is it increasing? Well, it seems like it is increasing, but we need to prove it. Okay, so the way to prove it is a sub n plus 1 minus n sub n, and this is 1 over 2 times a sub n plus 3, okay, if we expand this expression, minus a sub n. Okay, so this is 3 minus a sub n over 2, or in other words, 6 minus n sub n over 2, right? But now we have said that a sub n is always smaller than 6, so 6 minus a sub n is going to be greater than 0. So this is greater than 0, and the denominator is greater than 0, so this is greater than 0. A sub n plus 1 minus a sub n is greater than 0, so this is increasing. Okay, so this is a sequence that is bounded from above. It is monotonically increasing. So this theorem here, 3.25, every monotonically increasing sequence that is bounded from above, it converges to some limit. Okay, so we know that this sequence will have a limit. Okay, so let's call this limit a. A is the limit when n goes to infinity of a sub n. Okay? Well, let me erase this. Now, how do we find the limit of this sequence? We think it's 6, but the way to do it is, suppose we take limits in both sides, okay? The limit when this is true, and then this is the limit when n goes to infinity of a sub n plus 6 over 2, okay? Now the limit of a sub n plus 1 is the same as the limit of a sub n, okay? It's the same thing, okay? You can maybe think about it for 1 minute. So this is going to be called a, okay? And this limit is the same as the limit of the numerator divided by the limit of the denominator, which is 2. But in this case, this is the limit when n goes to infinity of a sub n plus 6 over 2, and this is a, okay? So if we take everything together, this is a equals a plus 6 over 2. Or in other words, 2a equals a plus 6, or a equals 6. Okay? So we have proven that this sequence is monotonically increasing. It is bounded from above by 6, and it converges to 6 by taking these limits here. Okay? Okay, next example. So suppose we have this sequence. A sub n is 3n squared plus 2 times n minus 1, and over 5n to the 4th minus 2n plus 7. Okay? So again, using the definition to compute the limit of this is going to be very, very hard, but we can do some tricks here. We can take the common factor to the greatest power in this. So this is a polynomial in n, as you can see. Okay, we can take a common factor for this highest degree here, which is n squared, right? So this is n squared, and then this is times 3 plus, and then 2 divided by n, right? Minus 1 over n squared. And the same in the denominator, but with n to the 4th. So this is 5 minus 2 over n cubed plus 7 over n to the 4th, right? And then n squared and n squared cancel each other out, and then you have 1 over n squared times this 3 plus 2 over n minus 1 over n squared over 5 minus 2 over n cubed plus 7 over n to the 4th, right? So if we want to compute the limit of this, the limit when n goes to infinity of a sub n, it's the limit of this 1 over n squared times the limit of this sequence. 3 plus 2 over n minus 1 over n squared, 5 minus 2 over n cubed plus 7 over n to the 4th, right? Well, now we know that this is going to 0, okay, because we saw that the limit of n goes to infinity of n to the p is 0 if p is smaller than 0, right? And this limit is 3/5, okay? You can compute it because this is the limit of the denominator, sorry, the numerator is 3 plus the limit of this, which is 0, the limit of this, which is 0, so this is 3 over 5 plus 0 plus 0, okay? So this is 0 times 3 over 5, or in other words, 0, okay? And actually, from this example, we can derive a general rule, which is this proposition here. It says, let a sub n be this quotient, alpha sub p times n sub to the p, plus alpha sub p minus 1, n to the p minus 1, plus, so a polynomial in n of degree p, over a polynomial in n of the degree q, okay? So the limit in general, and you can prove this using the same tricks that we have used for the same, previous example, is that if q and p are the same, then the limit of a sub n is going to be the quotient between the first two terms, okay? Because again, you can take the common factor of n to the p here, and everything else will be going to 0, and here 2 as well, but then n to the p and n to the q cancel each other out because q and p are the same. Okay, now if q is greater than p, this is the same as the example before, and then you get a term here that's 1 over n to the something because q is greater than p, and then the limit of a sub n is going to be 0. And then finally, if q is smaller than p, then you have a term, positive term of n in the denominator, and we know that that is going to go to plus infinity if the quotient, sorry, the coefficient is positive. Okay, so if alpha p b sub q is greater than 0, so this coefficient is positive, then the sequence will go to infinity, and if the coefficient is negative, this will go to minus infinity. Okay? So it's the same proof, the same tricks that we have done for the previous exercise. Okay? And finally, before we, final two things before we turn out to the same video, next video, some limits that are useful for computations. We will see how to derive some of them in the next videos, but you need to know these guys by heart. Okay, so the limit of the nth root of a for any positive number a greater than 0, it doesn't matter which one, this is going to be 1, the limit of this. Okay, even if what's inside is n, so this the nth root of n, the limit of this is also going to go to 1. Okay. Now the limit of a to the n is 0 if the absolute value of a is smaller than 1, and if it's greater than 1, it's going to go to plus infinity. Okay, so if a is greater than 1, it's going to be plus infinity. And then the limit of n to the r, with r a real number, divided by a to the n is equal to 0 for all a such that the absolute value is greater than 1. Okay, so that means that any polynomial n to the r is growing to infinity more slowly than the exponentials. Okay, but we will see more on that in the next lectures. Okay, and finally, the last result that I want to talk to you about is this theorem that we call the Bolzano-Weierstrass theorem. Okay, so these were two mathematicians. There was a German mathematician, Weierstrass, and Bolzano was an Italian mathematician. So sometimes the theorems are named after the mathematicians that proved them in the first time. Okay, so this every bounded sequence has at least one convergent subsequence. Okay, so the proof for this is really easy. Okay, so we know that every sequence has a monotonically increasing or decreasing sequence. Okay, this is one of the results, subsequence, sorry. We saw that before in the video. Okay, and we know that every bounded and monotonically increasing or decreasing sequence has a limit, right? Okay, so what you do is you have a bounded sequence, you extract from it a monotonically increasing or decreasing subsequence that we know exists, at least one. Well, that subsequence will have a limit because it's bounded and it's monotonically increasing or decreasing. Okay, so for instance, this classical sequence -1 to the n, right? We've seen it. It's non-convergent. It's going -1, 1, -1, 1. Well, if you take this subsequence 1 or the other subsequence -1, okay? So for all n, this is 1, and for all n, this is -1. Both of these sequences are convergent, okay? Okay, so that's the end of this video.